Welcome to week 6 of remote learning. This week, our topic is limits. Your quote homework assignment will be from section 10.3 from your textbook, and then you'll be required to take the limits quiz in Canvas. And like each week, my office hours are from 1 to 2 each day, Monday through Friday. Again, if you're struggling, please send me an email and I'm happy to set up a Google Meet to work with you. So kind of a cool picture. Could think of the sky is the limit. Some good shop jokes here for you. This is from the Grand Teton National Park in Wyoming. Never been there, but looks pretty cool. In your textbook, you can find this on pages 815 through 825. I'm going to kind of hit the highlights in my slides today, and if you need more instruction, then please refer to these page numbers in your textbook. So first, I want to consider the function y equals sine x divided by x. And my question is, what happens as x approaches 0? And so if you think about plugging in 0 for x, on the top you would get sine of 0, and we know that's 0. On the bottom we would get 0, and we know we can't divide by 0. So simply just substituting in the value of 0 does not give us an answer. So instead, we can look at the graph. And so here is a picture of the graph of sine x divided by x. And again, we have that same question, what happens as x approaches 0? And so it kind of looks like we're looking for that spot right there. So once again, if we look at this graph, it looks like that value is 1. The tick marks aren't shown for you there, but that value is 1. But we know that when we plug in the 0 for the x's, we ended up with 0 over 0, which we know is not defined. But if we look at the graph, we can tell that this y value is approaching 1 as x gets close to 0. So, summary of what I just said there. So it appears that the limit of sine x over x as x approaches 0 is 1. It says you can also look at a table to confirm your conjecture. Again, you guys know I like looking at tables, especially for visual learners. So here is the limit notation that we use. Again, we worked with limits already earlier in the year. So the limit as x approaches c of f of x equals L, and L is the limit, so some constant value. Again, there it is in quotes, the way I read that. This is a little bit different order than what I said, so it's another way you could say it. The limit of f of x as x approaches c is L. I kind of switch those around. And in notation form, we write it like this. So that L we're replacing with the number 1. Our f of x was sine x over x, and again, the x value that we were approaching was 0. This limit is one that occasionally will pop up in calculus and may be beneficial in some of your practice problems in your homework. All right, this says that the limit of a function refers to the value that the function approaches, not the actual value, if any. So like in the very first example that we looked at, we knew that we could not plug in 0 into the top and bottom because it gave us 0 over 0. But when we looked at the graph, we could see that as x was approaching 0, your y value was getting close to 1. So let's take a look at a graph. And in this graph, we want to focus on the limit as x approaches 2. So I'm going to fill in a little 2 right here. And I did not label the axes, but all of these are counting by 1, so that is 1 and that is 2. So if we want to talk about the limit as x approaches 2, that value is 2. And I want to kind of show you that in the picture. So as my x values are getting close to 2, both from the left and the right, the y values are getting close to 2. So this 2 right here is the y value. The x value that we see is here. But notice there is a hole in the graph. F of 2, let's write that out. If you look at the picture, f of 2 is equal to 1. So when x is 2, y is 1, not 2. So that's the value of the function at 2, whereas the limit is equal to 2. So the limit is 2 and the value is 1. Again, the limit is not 1. All right, so properties of limits. These are pretty self-explanatory, so instead of writing them all out in the PowerPoint, I decided just to give you a page reference in your textbook, and that page is 817. There's a chart there for you, and it pretty much says limits can be added, subtracted, multiplied by a constant, divided, and raised to a power. So I'm just going to write one example up here, and I'm going to focus on that limits can be added. Okay, so that's going to be my example. So for instance, if I had the limit as x approaches 2 of f of x equals 6, and I had the limit as x approaches 2 of g of x is equal to 3, then I could say that the limit as x approaches 2 of f of x plus g of x, and it is simple as taking each of the limits separately and adding them together. And so you may from that be like, oh yeah, those are kind of self-explanatory. But again, please look on page 817 at that chart. But again, I did not feel it was necessary to write all of that information out here. All right, we have one-sided and two-sided limits. We described these some when we were looking at asymptotes already, when we were studying rational functions. So just to review that notation, if we have a right-hand limit, that is written as the limit as x approaches c. And on the right side of your positive number, so it puts a little plus sign, kind of as it looks like an exponent. So of f of x equals c. Again, c is just some constant. And in the left-hand limit, we get the limit as x approaches c. And this time we have a little minus sign, because think your negative numbers are on the left-hand side of f of x equals, oh, sorry, I don't know why I wrote c there. Let's use L for limit like we were doing before. So right-hand limit has a little plus sign above the c. A left-hand limit has a little negative sign above the c. And then if we have what is called a two-sided limit, we just have the limit as x approaches c. There's nothing up there, a plus or minus, which means that we're approaching from both directions. And that limit is still some constant. So those are our notation, and we're going to look at some examples to make sure that you guys understand both the notation and how to find these. If I'm going too fast, again, please press pause as needed. So it says for a limit to exist, the function must approach the same value on both sides. We have to approach that same thing from the left and from the right. It says one-sided limits approach from either the left or the right side only. Again, a two-sided approaches from both the left and the right. So here we have another picture, and we're going to explore some limits. So we're going to start focusing at x equals 1. And so if we look at x equals 1, we can talk about the limit as x approaches from the left-hand side. And so as I approach, and I'm going to try to color coordinate here since we're not in the classroom together, since we're approaching 1 from the left, again, that's your x value. So we're coming in from this direction. So that y value is getting close to 0. Whereas if we approach from the right, the plus sign, so we're approaching 1 from the right, and that's this way, so that y value is approaching 1. But since those two limits are different, we do not have a limit at x equals 1. We do have a value, and that's f of 1 equals 1. But again, the limit does not exist because the left and right hand limits do not match. Again, if you notice, we got 0 for the left hand limit and 1 for the right hand limit, and those are not equal. So therefore, the limit as x approaches 1 does not exist. Again, we still have a value of the function, but we don't have a limit. All right, same picture. Let's look at x equals 2. So same order from last time. As we approach 2 from the left, so coming in from the left, my y value is approaching 1. If I approach 2 from the right, so coming from this direction, my y value is approaching 1. So therefore, the limit as x approaches 2, since those are the same, will indeed be 1. But what is the value of f of 2? Because notice there's an open circle there. So the value f of 2 equals 2. Again, we have this dot up here. So that's where this is coming from. And then lastly, the limit does exist because the left and right hand limits are the same. So this time, these are equal. Therefore, we do have a limit as x approaches 2, and it is 1. Even though the value, f of 2, is not 1, it is equal to 2. All right, let's do one more at x equals 3. So as we approach 3 from the left, my y value is approaching 2. As we approach 3 from the right, my y value is approaching 2. And if we notice this time there's a closed circle, so that point there means that f of 3 is 2. And then we see once again that because the left-hand limit and the right-hand limit are the same, then that means the limit does exist. So in this case, the limit and the value happen to be the same. So the limit as x approaches 3 is 2, and the value of the function at 3 is 2. But that does not have to be the case, as we saw in the previous example. Quick reminder of our rules, what I call them the 3 rules from Math 3. I did some abbreviating up on this slide, and I know we did our silliness in class about degnum and degden. So it says that the degree of the numerator equals the degree of the denominator. Then just a reminder, the horizontal asymptote is y equals the ratio of the leading coefficients of the numerator and denominator. If the degree of the numerator is less than the degree of the denominator, then your horizontal asymptote is y equals 0. And if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. And the reason I wanted to review these 3 rules is this will help us in determining the values of some of our limits. So when we are finding horizontal asymptotes, you may remember horizontal asymptotes are also called end behavior asymptotes because the horizontal asymptotes are telling us what our graph does on the end. So as x gets really large and as x gets really small. So as x is approaching positive infinity and x approaches negative infinity. And so those are actually limits that we are looking at. So here's an example of the graph y or f of x equals 1 over x. This is our reciprocal function. It's back in our pink packets, purple packets, I don't remember from the beginning of the year, but our 12 basic functions, hopefully you still have those. And so if we take a look at this, it says the limit as x approaches infinity is 0. And so again, I'm going to use highlighter here to hopefully make this show up. So as x is getting large, we can see those y values are getting close to 0. So as the denominator gets large, the value of the fraction gets smaller. So in other words, I always like to use food. Think of 1 pizza divided by everybody at Millbrook High School. Essentially, if we split that up, you're going to get nothing, maybe a small crumb. So it says there is a horizontal asymptote if the limit as x approaches positive infinity of f of x is equal to b, again b being some constant, or the limit as x approaches negative infinity of f of x equals b. So I did not include that one, but also if you notice here on the graph, as I approach negative infinity, your y values are also getting close to 0. So that is a horizontal asymptote, and you can see that based on the end behavior on the left end and the right end. Again, b is just some constant. In this case, it was 0. So vertical asymptotes, again, we described those when we were studying our rational functions. It says the line x equals a is a vertical asymptote of the graph of the function y equals f of x if either the limit as x approaches a from the right of the function is approaching positive or negative infinity, or the limit as x approaches a from the left of the function is positive or negative infinity. So it says, in other words, after simplifying a rational function, set the denominator equal to 0 and solve for x. So that's how we find vertical asymptotes in the event you have forgotten. And then my friendly reminder at the bottom says, don't forget to always check for holes first. And hopefully you remember holes occur when you have that common factor in the numerator and denominator of a rational function. So that's just a quick little review at the bottom, kind of the more formal definition of vertical asymptotes in the box at the top, and again using limits to describe the behavior of the graph near the vertical asymptotes. So again, still looking at that same function, our reciprocal function f of x equals 1 over x. To describe that, says as the denominator approaches 0, the value of the fraction gets very large or very small. Sometimes I have a really hard time thinking about this. So thinking like 1 divided by 0.000001. So you're dividing by a very small amount, and that actually gives you a really large number. So it says if the denominator is positive, then the fraction is positive. And so we see here, it says the limit as x approaches 0 from the right. So if we have 1 divided by a positive number, then we are going to get positive infinity. And so again, this limit we can see here as we are approaching 0, my graph is going up. If the denominator is negative, then the fraction is negative. Think 1 divided by a negative number is going to be negative. So for this one, I'll highlight this one in orange. And so as your x values get smaller and smaller and smaller, notice your y values are getting smaller, approaching negative infinity. So what this shows us is that we do have a vertical asymptote at x equals 0. And as you see, it's drawn in there with the dotted red line. And to finish up, I'm going to do one example. Again, you will find lots more examples in your textbook, but trying to keep this video shorter this week. Says, find the limit as x approaches infinity of 5x plus sine x over x. So I'm going to use some of those properties that you found on page, I believe it was 817. If you think about this rational function, I have 5x plus sine x over x. You have to remember that both 5x is being divided by x and sine x is being divided by x. So I can split this up into two separate fractions. Then the first fraction, 5x divided by x, we can simplify, and we see that the x values will cancel out. And now I'm left with the limit as x approaches infinity of 5 plus the limit as x approaches infinity of sine x over x. Again, that's kind of the reverse of what I showed you using that addition property for limits, because I kind of split it up into two separate limits. If you remember from the beginning today when we looked at sine x over x, that graph looks something like this. Again, a rough sketch. You can go back and look at the other one. But this part says, as x approaches infinity, what is happening to my graph? And so we're looking way out here. And again, it's a little bit hard to see, again, based on my sketch for one reason, but that value is actually approaching 0. And the limit as x approaches infinity of 5, like it doesn't matter, 5 is just the number 5. So we get 5 plus 0, which is just 5. So the limit of this crazy looking problem is essentially 5. Again, if you're not sure, you could look at the entire graph. You could also look at your table to confirm that value. If you're having doubts and thinking back to that first question and thinking like, wait a minute, she said it was 1 then. That was the limit as x approaches 0. Now we have the limit as x approaches infinity. Well, that's it for this week. Your homework is from section 10.3 on pages 826 through 27. So I've given you kind of an array of questions here. Again, odds only, so you're able to check your answers in the back of the book. Again, please consult your textbook for more examples. But since this is not the first time you've seen limits, I didn't want to spend too much time doing examples and boring you guys to tears. And then secondly, you'll need to take the limits quiz in Canvas. It's a short one. I think it might only be 5 questions this week, just to make sure you understand. But anyway, hope you guys have a great week. Please reach out if I can help you in any way. Take care.